All right, today's video is going to be about properties of integrals. So basically, we can add functions, we can subtract functions, we can multiply functions, all those ideas of, how do you manipulate something within mathematics. Well, here we're going to talk about when we're presented with an integral, okay, integral being that elongated S, right? So when we're presented with an integral, what can we do with them? How can we work with them? How can we help ourselves to be able to evaluate them? What types of tips and tricks do we have? And how do they kind of relate with one another based on what you're seeing on a graph, what you're finding, etc. So generally, we're assuming that A is less than B when you're reading from left to right. So if you were looking at a graph, A would be to the left of B, but that's not always the case, all right? But for ours that we're going to talk about here, A is to the left of B, even if they're super close together. If they're both in negative territory, one's in positive, one's in negative, you get the idea. So, sum and difference. We've seen this before. If I want to take the integral from a to b of f of x plus g of x, I can take the integral from a to b of f of x dx and add to it the integral from a to b of g of x dx. So we've seen that before, kind of like with taking the derivative, right? We can take the integral or sum up the area of each piece individually and then add their integrals together. Same thing is true if you were subtracting. You could find the area underneath f, or trapped by f, bound by f, and you could subtract the area bounded from g. The constant multiple rule. Oh my gosh, this thing keeps coming back to haunt us. When we have k, a constant that's multiplied with our function. Again, this is a constant multiple, so k is not something that varies. You can take the k out in front and then do the summation of your function. So the integral from a to b of f of x dx. The reason this works is if we think about k being a vertical stretch of a function, or a vertical shrink for that matter, when we take it out, it would be the same vertical stretch or shrink of the area that you are collecting. Reversing the integral, okay, so reversing the integral, if I was summing from a to b of g of x, that is the reverse of summing from b to a of g of x dx. So if we think about that from an area collecting standpoint, right, so if here's a and here's b, maybe I have some function g of x. If I start at A and I collect all of the area going this way, it's the opposite of if I had started at B and collected this way. And we'll look more at that in just a few minutes. Zero length interval. Sorry. All right, better. Zero length interval from A to A. Well, if I'm supposed to sum from, let's say, 2 to 2, on a graph, I'm collecting the area from 2 until itself. Is there any area to be collected? No. There's no area there, right? So we're looking for a finite area. If you don't have an interval, if we're talking about just from one value to itself, okay, we don't have any area. Adding intervals. So this is different than adding integrals. We are adding intervals. So I'm looking to collect the area from A to B underneath some function f of x. And I'm supposed to add to it the area from B to C, the area underneath f of x. Well, a more efficient way to do that would be to just go from A to C, right? I'd collect the area from A to B, and then I'd add to it the area from B to C. Well, come on now, Schwartz. Why don't you just sum from A to C? Make your life a little bit easier, right? So the way this one works is you want to make sure that your upper bound of the one is equal to the lower bound of the next one that you're adding. So I like to think about this as I'm going from A to B, right on through, from B to C, okay? Quick reminder about what does it mean to find the absolute value of a function. The absolute value of a function is written like this. So what that means is we're going to take all of our y values, our outputs, right, f of x, and we're going to make them positive. So anything that was below the x-axis is now going to flip above the x-axis. Well, all of this was already above the x-axis. These points then are all going to flip up above. So if I were to integrate from 0 till 8, the absolute value of f of x dx, what I'm finding is this green area right here. That is not the same as the absolute value of the area. Okay, and the reason for that is in this case, all of our rectangles that I'm collecting, right, from 0 until 8, should keep that in green, all of this stuff that's shaded in green, these are all positive widths and positive heights, and positive widths and positive heights, and positive widths and positive heights, even over here, positive, 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 positive. All of this is positive, and then you're going to take the area of that. If I think about what the graph represented before, right, this graph, if I wanted to find the area trapped in red, actually I'm going to do blue. If I just wanted to find the integral from 0 to 8 of f of x dx, switch up my colors here a little bit. If I wanted to find the area of this blue regions, right, this area, this trapezoid, would have positive area, but this would actually have negative area. Because in this one, I'm traveling positive, 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 positive. But now I start to go positive widths and negative heights, and positive widths and negative heights, and positive widths and negative heights. So the area of this triangle between 5 and 8, because we're going from left to right, 5 to 8 would end up being a negative area. So we would end up with some sort of a positive plus some sort of a negative. And so if I then took the absolute value of this whole thing, that's not necessarily equal to the area of the whole thing being positive to begin with. All right, think about collecting the area and the sign of each rectangle. So what I mean by that is if you are traveling to the right and drawing up to meet your curve, well, that's going to be a positive width and a positive height, which means that your area is positive. If you are, quote, traveling to the right, but your graph falls below the x-axis, well, now you have a positive width, positive x's, but a negative height. Well, a positive times a negative results in a negative. If your integral, instead of reading from left to right, let's say your integral was from 8 to 5, well, you would start at 8 and you'd go backwards on your x-axis, and then if your graph was above, we would have traveled negatively in the x direction, positively in the y direction, and a negative times a positive makes a negative. Last one then, I could travel backwards and have negative heights. Well, negative x and a negative y multiplied together, we would actually count this as positive area. Okay, so we want to think about collecting that area. Okay, and if you're to draw in kind of a representative rectangle, what would your width look like? What would your height look like? And take into consideration positives and negatives. We're going to go through this, evaluating from a graph, evaluating using geometry, evaluating using a table, and using those properties that we just talked about. So in class, we're going to go through an example of each of those. There is a video posted, an older video, that has some of those sample problems worked out that you can use. But for right now, we just need to make sure you have all of these properties down. A reminder, these are not necessarily shortcuts. We're going to get to a shortcut. How do we avoid that whole limit summation thing? We'll get there in a little while. Right now, we want to think about these integrals representing the area between a curve and the axis, right? We want to think about positive areas, negative areas. How can we use geometry to help us? And how might we use the limit summation until we eventually get to those desired shortcuts?